let's talk about the ratio test. But actually, before we talk about the ratio test, let's talk about what it really is built upon. So talk about geometric series for just a minute. So everyone can see, move this a little closer. Yeah, all right. So geometric series. Welcome. So for example, thank you. Let's say we had the following geometric series. I don't know, 60, 20, 20 over 3, 20 over 9, 20 over 27, etc. And certainly one way you can identify the ratio for a geometric series is by taking the next term divided by the previous term. So we can see 20 divided by 60, or 20/3 divided by 20, or 29ths divided by 20/3. Each of these is equal to 1/3. And that pattern continues forever and ever because the ratio is 1/3. So here, that is our ratio. And we would be able to see that this geometric series, I should say, right, this is actually the sequence. The geometric series would be the sum. And there's a lot of ways I could write this. I'm going to write it as the sum from n equals 1 to infinity of 60 times 1/3 to the n minus 1. That geometric series definitely converges because our R value is between 1 and -1. So this is kind of what's going to lead us into talking about the ratio test. So to find the ratio R for any geometric series, we can, of course, divide the next term, probably not the next, we can divide any term by the previous term. Okay, so we can write this generally. Right? If we have some series that consists of the sequence A1, A2, A3, A4, all the way to some A sub n plus 1, et cetera, et cetera, et cetera. Well, our ratio could be any quotient of next term over previous term, meaning the ratio would be A2 over A1, A3 over A2, A4 over A3, all the way to A sub n plus 1 over A sub n. Each of these would be equal to the ratio. Okay. Well, that's kind of the idea behind our next test. So we're always like, let's see if we can keep things in. Jason, see that all right? I feel like it's never looks great. It's a little bit visible. I mean, I assume you would tell me if it wasn't. So the idea for the ratio test is that while the series, thank you, isn't actually geometric, eventually it mimics a geometric series. Let's look at an example. So let's say, let's keep things in order here. Yeah, that's all right. Sorry, it's always so many things. Okay, so let's say we had something like this. The series or sum from n equals 1 to infinity of n squared over 3 to the n. It's definitely not geometric, right? You can see that from the way the formula is. You don't have just some number raised to the nth power. You can also see it by writing out literally the first 3 terms. If I write out the first 3 terms, I'm going to get 1/3 plus 4/9 plus, and let's see, if I plug in 3, I'm going to get 9/27 plus plug in 4, I'm going to get 16/81, and so on and so on and so on. We're going to write a few more terms over here, so leave yourself some room if you're writing this down. And you can see that this is certainly not geometric. The ratio of, say, 4/9 divided by 1/3, which equals 4/9 times 3, which is 4/3, that's not going to be the same as 9/27 divided by 4/9, which is equal to 9/27 times 9/4. So that's terrible. Right? Definitely not the same. So it's not geometric. But if you go way, way out, say like to the 1,000th term, and you get 1,000 squared over 3 to the 1,000th power. And then the next term is 1,001 squared over 3 to the 1,001 power, and so on. This is starting to behave very geometrically because essentially this next term, the numerator hasn't changed that much. I know, I mean, 1,001 squared, okay, it's a little bit bigger than 1,000 squared. It's like 1,000 bigger. But when you compare that to dividing by the next power of 3, it's really kind of not a big difference. So essentially from here to here, you're essentially multiplying by 1/3. Not exactly, but pretty close. And if you go way, way even out further to like the AN term, which is going to be n squared over 3 to the n, and the AN plus 1 term, which is n plus 1 squared over 3 to the n plus 1, we have the same idea. From here to here, we're essentially multiplying by 1/3. So that's the idea, is that the ratio here, while there isn't actually a ratio, this series essentially starts to behave like it is geometric as you move way out to the end terms, to the terms where you are far further out. And we can even think about finding the ratio R. So R, well, it's going to be, let's look at this term divided by that term. So the 1,001st term divided by the 1,000th term is going to be 1,001 squared divided by 3 to the 1,001. So here's something I would encourage you to get used to doing. When you divide a term by the previous term or two terms together, instead of actually writing out the division, the thing you're dividing by, we just want to multiply by the reciprocal. That's what's going to happen all the time when you're doing the ratio test, also when you're doing the limit comparison test. So instead of dividing by 1,000 squared over 3 to the 1,000, let's multiply by 3 to the 1,000 over 1,000 squared. Cool with that? Really, we're just doing, we're doing 1,001. And now I'm going to write it all out over 3 to the 1,001 divided by 1,000 squared over 3 to the 1,000. But then we're doing a copy dot flip or a flip and multiply, or whatever you want to call it, right? We're dividing by the thing, so we're multiplying by the reciprocal. And when we simplify this, 3 to the 1,000 over 3 to the 1,001 is just 1/3. And 1,001 squared over 1,000 squared, well, let's simplify. That's 1/3. And here I can write this as 1,001 over 1,000 squared. 1,001 over 1,000 is 1.001. And if you square that, it's even smaller. I guess it's slightly bigger, apologies. It's like 1.002001, but it's pretty close to 1, right? This here, very close to 1. So this is essentially 1/3. And we can see that would be true for further terms, right? And the next term would be, the next ratio would be even closer to 1/3 and closer and closer. So these terms out here, the ratio between them is really, really getting very close to 1/3. So this series acts like a geometric series. with R equal to 1/3, which means we think it should converge or diverge. If the ratio is 1/3, should it converge or diverge? What do you guys think? Anybody? Anybody? I know you guys know, you just don't want to say words. Thank you. Yes, it converges, right? Because when the ratio is between 1 and -1, it converges. So the actual test is to do the following. We're going to look at our series, and we're going to find the quote unquote ratio equal to the limit as n goes to infinity of the next term over the previous term. And then usually there's also some absolute values there, which we'll talk about a little later, but you don't need them here because all the terms are positive. Well, we just did that. Well, let's do it again. That's going to be the limit as n goes to infinity. Well, actually, we didn't. We did that for the 1,000 and first over the 1,000. So now we're going to do it for the n+1 term over the n term. So it's going to be my n+1 term. So it's going to be n+1 squared over 3 to the n+1. And then instead of dividing by the a sub n term, we're going to multiply by its reciprocal. So we're going to multiply by 3 to the n over n squared. It's just good practice to get used to doing that because you're going to do it a lot. Okay. In the same sort of way, when you're doing a ratio test, you typically want to combine the similar things together, meaning instead of writing this fraction times this fraction, I'm going to rewrite this as n+1 squared over n squared times 3 to the n over 3 to the n+1. This simplifies just 1/3. So I have the limit as n goes to infinity of 1/3 times, you could multiply that out. You could multiply n+1 squared and get n squared plus 2n+1 over n squared. And this rational function, where the top and the bottom have the same degree, the limit is the quotient of the leading coefficients. So we're going to get a 1/3 times 1, which is 1/3. Ideally, we should be able to look at this and see that, oh, the top is n squared plus lesser terms, the bottom is n squared. So the limit of that is going to be 1/1, which is 1. So what does that mean? That means our series converges because it is essentially or similar to a geometric series with a ratio of 1/3. So those are kind of the nuts and bolts behind the ratio test. You're literally taking the ratio of the n+1 term over the n term to see if it's getting closer and closer to some actual ratio like a geometric series. So actually, I think it's really important for when you do the ratio test to remember that it's like a geometric series, because that'll help you remember when it converges and when it diverges. Just like a geometric series converges if the ratio is between 1 and -1. The ratio test will tell you a series converges if the ratio is between 1 and -1. And just like it diverges when the ratio is bigger than 1, the ratio test will say it diverges if it's bigger than 1. There's a small difference if it's equal to 1, but we'll talk about that. So here is the ratio test. So for a series, sum from whatever of a sub n, if the limit as n goes to infinity of the n+1 term over the n term, usually we put some absolute values around that. If that's equal to r, then one of 3 things can happen. Thing 1, the series converges if this ratio is strictly less than 1. The series diverges if this ratio is strictly greater than 1. And unfortunately, the test is inconclusive if R is equal to 1. So it doesn't mean you just stop there. It literally means like if the ratio test gives you 1, we need to do other things, right? It means you don't know. It could still converge, it could still diverge. It's kind of like when you do the nth term test and the limit is 0. The series could converge, the series could diverge. We have to do more work. Question so far? Oh wait, so we have to do both? I guess I'm not sure what your question is there about having to do both. You're welcome to expand upon it. But all I'm saying we have to do currently is we have to, so the thing I did before on the previous page, I find the limit and what we did. So this before part is not something we have to do. This was more of just an explanation as to why the ratio test actually works the way it does, because you're essentially finding the ratio that is like the ratio of a geometric series. And if it's less than 1, like the ratio of a geometric series, then we get convergence. If it's bigger than 1, we get divergence. Yeah.
For 3n over 3n plus 1, what was the calculations to get 1/3?
Ah, that's an excellent question. So one way to see this, I think there's 2 good ways to see it. You can say 3 to the n over 3 to the n plus 1 is 3 to the n over 3 to the n times 3. Because if that's a 3 to the 1, we would add those powers. And then you can cancel a 3 to the n and a 3 to the n. Or if you prefer, you can say that this is equal to, you do that thing where you subtract the powers. This would be 3 to the n minus n plus 1. And then that'd be n minus n to 0, and then a minus 1 would be 3 to the negative 1, which is 1/3. You're welcome. No, we really, so to answer your question, we really do need to find the limit. This here was more, again, the previous work we did was more just explanatory, but the actual test, the ratio test here, says we actually have to find this limit here. And if that limit is less than 1, convergence. Greater than 1, divergence. Equal to 1, do something else. Okay, so let's look at some examples. Like the following. I should actually point out. So it usually makes sense to try the ratio test. Doesn't mean it's always going to work. It usually makes sense to try the ratio test if you see one of 2 things. Either something raised to the nth power or something with a factorial. Those are 2 really good indicators that you probably should try the ratio test, and it'll probably work. Not all, right? There's no guarantees. Nothing's going to work all the time, 100% of the time, right? Things don't always work all the time, but most of the time, if you see one of these 2 things, it's probably a good bet that the ratio test is what you should try. So let's look at the following example. Let's look at the sum from n equals 1 to infinity of n to the 4th times 5 to the n plus 1 over n factorial. So all the signs that we should use the ratio test, especially the factorial. The factorial, there's not a lot of other tests that really work well on it. So if you see a factorial, especially, ratio test is usually what we are hoping works, because other things just don't work that well. So we're going to find the limit as n goes to infinity of the absolute value of the n plus 1 term over the n term. And again, here's the work. Here's where I would start. I would write this as the limit as n goes to infinity, the a sub n plus 1 term. So I'm going to plug in an n plus 1 for every n. So I'm going to have n plus 1 to the 4th times 5 to the n plus 1 plus 1, which, yes, you could write n plus 2, but I'm trying to show all the steps, over n plus 1 factorial. And then instead of dividing by this, right, this here is, that's our a sub n. Instead of dividing by that, let's multiply by its reciprocal. N factorial over n to the 4th times 5 to the n plus 1. And then, yes, technically there should be some absolute values here, but I think I can see that every term here is positive, so we can just drop the absolute values right away. So if you can see that all the things are positive, feel free to just drop the absolute. The only time you really need them is when you have something that's alternating, like you have a negative one to the n, and then you actually need it for a second. It's still pretty easy to get rid of them if you want. Okay, just like before. Oh, question.
For when you on the limit part, when you flip it, why isn't the, I don't know, it's called with the n with exclamation mark?
The n factorial.
N factorial. Why isn't there a +1 for the second?
So this here, that here is your a sub n plus 1. And this here is your 1 over a sub n.
Okay.
All right, so now, just like before, we're going to combine the like things together. So I'm going to write this as the limit as n goes to infinity of n plus 1 to the 4th over n to the 4th. And then 5 to the n plus 2 over 5 to the n plus 1 times n factorial over n plus 1 factorial. This is definitely what we want to do. And then we want to simplify. Now, this first part doesn't really simplify. N plus 1 to the 4th over n to the 4th. Well, there's one thing you could do. There's two things you could do. The thing we should do is we should write that as, I think we should write it as n plus 1 over n to the 4th. That's probably the most nice thing to do. 5 to the n plus 2 divided by 5 to the n plus 1 is going to be 5. We have one more multiple of 5 on top that we have on bottom. Again, you could do the thing where you either subtract the powers, n plus 2 minus n plus 1 is just 1, or you could say it's like 5 to the n times 5 squared over 5 to the n times 5 to the first, and then those cancel, and then 5 squared over 5 to the 1 is just 5. Now the n factorial over n plus 1 factorial. This is a thing you're going to see a lot, and it's not terrible once you get used to seeing it. But let's look at a quick example. What if we had 4 factorial over 5 factorial? What does a factorial even mean? It means 4 factorial means 4 times 3 times 2 times 1. And 5 factorial means, I remember the first time I saw it, I was like, I have no idea what that is. What is this exclamation point? Is this an exciting 4? No, it's 4 factorial. It's not exciting at all. But 5 factorial means that. So if we have 4 times 3 times 2 times 1, or 5 times 4 times 3 times 2 times 1, what are we left with? Just a 1/5. Another easier way of maybe thinking about this is 4 factorial over 5 factorial is 4 factorial over 5 times 4 times 3 times 2 times 1, which is 4 factorial. And then those cancel because they are the same. You can't just cancel out factorial symbols, though, just like you can't cancel out square root symbols, right? The square root of 9 over the square root of 4 doesn't equal 9/4, right? We can't cancel out functions, essentially. But this is 1/5. So the way to deal with this is to think of it as n factorial over n plus 1 times n times n minus 1 times, the remaining part is n factorial. And then those are going to cancel. Interesting. So a couple things you could do here. That's interesting. That's not all right. Is let's just take the limit. So as n goes to infinity, what's going to happen to this n plus 1 over n? Where's that going to go to? 1. So we're going to get 1 to the 4th times 5 times 1 over n plus 1, which is going to go to 0. Alternatively, if you really wanted to, you could have canceled an n plus 1 here with an n plus 1 there, but you don't need to do all that work. This is less than 1. So our series converges. So the sum of from n equals 1 to infinity of n to the 4th and 5 to the n plus 1 over n factorial converges. Because our ratio is essentially 0. If you go far enough out, the next term is so much less than the previous term. Yeah, that's fun, but not really necessary. There are some fun, we'll see. Maybe we'll have time for that. I like fun things, but we should devote our time to. So let's look at a couple more examples. Let's say we wanted to look at the sum of 2n factorial over 3 to the n times n factorial squared. I didn't give a starting place because you don't really know where you're starting to ask, does this converge or diverge? This one's going to be a little messy, but it's definitely a ratio test kind of problem, right? There's nothing else we should be trying here other than the ratio test. So we're going to do the limit as n goes to infinity of, all right, so 2n factorial is a little tricky when you're plugging in n plus 1. Well, let's just be careful. So I'm going to have 2 times n plus 1 factorial over 3 to the n plus 1 times n plus 1 factorial squared. And then times 3 to the n times n factorial squared over 2n factorial. That looks messy. Again, we're going to group terms together. We're also going to kind of simplify a little bit. So let's see what we mean by that. I'm going to write this as the limit as n goes to infinity. Of course, so you should get really comfortable with seeing 3 to the n over 3 to the n plus 1 and saying that's 1/3. And then, all right, 2n plus 1 factor, 2 times n plus 1 is really 2n plus 2 factorial over 2n factorial. And then we also have an n factorial squared over an n plus 1 factorial squared. And this is where it might be worthwhile actually writing a couple of things out. So let's see what happens. We have the limit as n goes to infinity of 1/3 times, so 2n plus 2 factorial. Let's start writing things. It's going to be 2n plus 2 times, I should give myself more room. Let's be realistic here. So we're going to have a 2n plus 2. And then what's the next smallest integer? Right. And then, right. And it keeps going. And then for 2n factorial, it's going to start at 2n. And then 2n minus 1, and so on and so on. So all of the things after 2n plus 1 are going to cancel. So this happens a lot when you have like a 2n factorial, you actually get 2 terms left over after you cancel all the things in the ratio test. And then for n factorial squared over n plus 1 factorial squared, I have an n factorial times an n factorial. And on the bottom, I have an n plus 1 factorial times an n plus 1 factorial. And we just saw from the last question that when you have n factorial divided by n plus 1 factorial, that leaves you with the 1 over n plus 1. So this part here, this is going to be a 1 over n plus 1, and this is going to be a 1 over n plus 1. So let's see what we're left with. We're left with the limit as n goes to infinity of 1/3 times 2n plus 2 times 2n plus 1 over n plus 1 times n plus 1. All right. That limit is certainly findable. What's the degree on top? If you multiply it at the top, what would the highest power be? I know my writing is not excellent. If you multiply it at the top, I think you'd have an n squared. Multiply it at the bottom, you'd have an n squared. What's the leading so we have same degree on top and bottom. We know the limit is the quotient of the leading coefficients. What's the leading coefficient on the top? It's more than that. It's that. Yeah, it's 4. It's 2 times 2. What's the leading coefficient on the bottom? Well, depending on how you're looking at how I've written it, you could either say 1 or you could say 3, right? Because there's a 3 times the 1. So there's my limit, which means, well, that's greater than 1. So we have divergence. So this series eventually starts acting like a geometric series whose ratio is 4/3. Which seems surprising because it seems very bizarre, but that's what we're getting. Yeah, let's look at one more. Okay. Question, you guys look like you might have, yeah.
For the, I'm just confused how they cancel out the n factorial with the n plus 1.
Sure. So I was referring back to the problem we did just before, but we could also write it out. N factorial times n factorial over n plus 1 factorial times n plus 1 factorial. What I'm really doing here is I'm saying,
Was it like what we did before with like the n plus 1 and then n plus 1 factorial?
right, the n plus 1 factorial is n plus 1 times n times n minus 1 times n minus 2 times n minus 3 times n minus 4, which is just n factorial. And then we have it again. N plus 1 factorial is n plus 1 times n minus 1 times n minus 2 all the way down. And so those cancel and those cancel. We're left with an n plus 1 times n plus 1 at the bottom. But yeah, this type of canceling happens a lot. So I want you all to be very, very, very comfortable with saying that this is true. N plus 1 n factorial divided by n plus 1 factorial is just 1 over n plus 1. Happens a lot. While we're on the topic of factorials, just as a point, although it's going to come up in a few days, but not right now. 3 factorial is 6. 2 factorial is 2 times 1. 1 factorial is 1. 0 factorial is 1 by definition. It needs to work that way because we all need all the rules of things to work that way. This is going to come back a little bit later, but it seemed like a good time to mention it right now. All right, let's look at one more example. I should also say all these examples, we've determined that if a series converges, great. We haven't actually seen what it converged to, right? And we can't for most of them, right? There's just no finding what a series converges to. The only types of series we know how to find what they converge to are geometric or telescoping if they converge. That's kind of it. No other series we really have the ability to determine without like a lot of work what they converge to. This next one is an exception to that. So today we have the sum from n equals 1 to infinity of n over 4 to the n. Again, ratio test is a great test to use here. So ratio test, we're going to take the limit as n goes to infinity of n plus 1 over 4 to the n plus 1 times 4 to the n over n. Once again, we're combining the things that go together. So that's going to be the limit as n goes to infinity of 4 to the n over 4 to the n plus 1, which is just 1/4, times n plus 1 over n. That's 1/4. And we know the limit of this n plus 1 over n is just 1. You're going to see that kind of thing a lot too, where you have n to a power plus some stuff over n to the same highest power. That limit's going to be 1. That's equal to 1/4, which is less than 1. So we get convergence. Interestingly, this series is one you actually could find what it converged to if you wanted to. It's not super important, but it is kind of neat. And it's nice to see neat things sometimes as opposed to just boring math all the time. So let's see a neat thing for a moment. You probably don't need to write all this time if you don't want to, because it's probably not super. I've seen people ask this as an extra credit question once or twice, but most of the time this doesn't pop up. But let's see what we mean here. So if I start writing out terms, let's see what we get. The sum from n equals 1 to infinity of n over 4 to the n is 1 over 4 plus 2 over 4 squared plus 3 over 4 cubed. Let's go 2 more terms. 4 over 4 to the 4th, 5 over 4 to the 5th. Okay, now we're gonna do something tricky. So watch this. I've got 1/4 plus 1/4 squared plus 1/4 cubed plus 1/4 to the 4th plus 1/4 to the 5th, etc. And then plus, well, I've used up my 1/4, so I don't have any more of those, but I still have a 1/4 squared. And a 1/4 cube. Actually, I have 2/4 cubed, but I'm going to use one of them. Plus 1/4 to the 4th, plus 1/4 to the 5th. And then 1/4 cubed, plus 1/4 to the 4th, plus 1/4 to the 5th. And then so each of these, so do I have all the things I need? Let's see, I have a 1/4, I have a 2/4 squared, I have a 3/4 cubed, I have a 4/4 to the 4th. I have, if I kept going, I would have a 5/4 to the 5th. I can keep doing this forever. But look, each of these is a geometric series in its own right. This is a geometric series. For this first geometric series, what's the ratio? What's the starting term? So this first geometric series is equal to 1/4 over 1 minus 1/4. Okay, for this second geometric series, what's the ratio? Still 1/4. What's the starting term? And for this next one, the ratio is still 1/4, but now the starting term is 1/4 cubed. And I'm adding all these together. So check this out. If we add all of those together, 1/4 over 1 minus 1/4 plus 1/4 squared over 1 minus 1/4 plus 1/4 cubed over 1 minus 1/4. And we do that forever. Well, look, I can factor out the 1/1 minus 1/4. And I'm going to multiply by a geometric series. 1/4 plus 1/4 squared plus 1/4 cubed. So that's going to equal 1/1 minus 1/4 times 1/4 over 1 minus 1/4. It's kind of cool. Kind of, you know, in the math world, right? So we end up getting 1/4 over 3/4 times 3/4, which we could simplify as 1/4 times 16 over 9, which ends up equaling 4/9. So it is neat to see that there are other types of series that we can actually find what they converge to. There's not a lot, but there are some. So this series actually does converge, and it converges to 4/9. Who knew? How interesting. Okay, so oddities aside, let's keep going. You want to know more about that? I should come to office hours sometime. I could talk forever about it. I'm sure you'd be all thrilled. Okay, not really. I mean, I could talk about it for a long time. You wouldn't be thrilled, I doubt. You might be. It's kind of interesting. I remember actually when I first saw that problem, you can actually do it for any power of n. So like for n squared over 4 to the n, you can also find what it converges to, but you have to find what the n over 4 to the n converges to first. And so it's like this whole recursive thing where the next one's built on the previous one, and I wrote like the whole thing about it. It's like I was a little involved with it for a while. It was okay. So let's say we have the following series. The sum from n equals 1 to infinity of m plus 1 over 2m plus 3. And just like before, well, kind of like before, it's starting to behave kind of geometrically. If we look at our terms, the first term is 2 over 5 to the first. And the next term is going to be, I plug in 2, 3 over 7 squared. And the next term is going to be 4 over 9 cubed. And if we go way, way out, we're getting like 101. If I plug in 100 over 203 to the 100th power. And then the next one's going to be 102 over 205 to the 101st power. So each next term is looking a lot like the previous term, right? 101 over 203, that's pretty close to 1/2, but it's being raised to the next highest power. So this is kind of like, this term here is essentially 1/2 to the 100th power. And this term here is essentially 1/2 to the 101st power. So in a very, very similar way as the ratio test, this series starts to behave or act like a geometric series with R equal to 1/2. And if you wanted to, no, the ratio test would be terrible to use here. You could probably make it, well, you might be able to make it work. But instead, what we're going to do is we're going to talk about the root test. So the thing you should remember about the root test is it's just like the ratio test. You're doing a limit, and if the limit is less than 1, the thing converges, and if the limit is bigger than 1, the thing diverges. So I really strongly encourage everyone to pair the ratio test and the root test in your head. They're virtually the same, except for their execution, but the results are the same. If the limit's bigger than 1, diverging because your ratio is larger than 1. If the limit is less than 1, the series is convergent because your ratio is less than 1. So in this particular case, we're going to look at the limit as n goes to infinity of the nth root of the absolute value of the nth term, which, if it equals a ratio, is going to equal some ratio, and if the ratio is less than 1, the series converges. If the ratio is larger than 1, the series diverges. And sadly, if the ratio is equal to 1, the series, we don't know. Yeah.
Like when we were talking about the ratio test, what we
So specifically, if you see the entire thing raised to the nth or to the nth squared or to the nth to some other, like if you see something, all of it raised to the n, and then maybe there's more or not, that's a really good time to use the root test instead, because it's going to work a little nicer. We could try to use the ratio test here, but it's going to get pretty ugly. I'll show you in a second, but let's look at the root test first. So if we apply the root test, we take the limit as n goes to infinity of the nth root of n plus 1 over 2n plus 3 to the n. First of all, this is almost never the way I like to write it. I would prefer to write this as the limit as n goes to infinity of n plus 1 over 2n plus 3 to the n to the 1 over n power, because the nth root is the same as the 1 over n power. And that's really typically the way most people write it. Notice I dropped the absolute values because all my terms are positive. I didn't even talk about it, right? It's not there because all the terms are positive. Here, the n to the 1 over n, that multiplies to 1. So we're just taking the limit as n goes to infinity of n plus 1 over 2n plus 3, which is equal to 1/2, which is less than 1. So we get convergence. So that series converges. Really, so here's the thing about the nth root test. It's actually a more powerful test than the ratio test, meaning there are series that can be shown converge using the nth root test, but not the ratio test. Whereas if the nth root test works for something, or sorry, if the ratio test works for something, the nth root test should also be able to show that it's convergent. But it might be a really calculationally difficult way to do it. So the nth root test is nice if it's nice, and the ratio, but we often use the ratio test more. Here, if I tried to, so technically it should be true that the ratio test should work for this. Oh no, that's not true. Sorry, back it up. If the root test works, the ratio test might. If the ratio test works, the root test has to. Yeah. So it may or may not be the case that the root test would even work here. And if you start looking at the root test for this, just so we can kind of see why you might not want to use it. I mean the ratio, thank you. Sorry, my brain's saying all the R words and yeah. So if we try the ratio test for this, things are going to get gross, I think. By looking at that, it's going to be the limit as n goes to infinity of n plus 2 over, I'm going to simplify things as I go. 2 times n plus 1 is 2n plus 2 plus 3 is 2n plus 5 to the n plus 1 times the reciprocal, which is going to be 2n plus 3 over n plus 1 to the n. That looks bad. That looks like I'm really not going to want to do that. Like so much no. You can make this work, I bet. So if I think about this for 1 hot minute, here's what I've got. I've got n plus 2 to the n plus 1 times 2n plus 3 to the n over 2n plus 5 to the n plus 1 times n plus 1 to the n. Yeah, we could totally make this work, but you have to, it's not the best. So here's my thought process. If you multiplied out the top, it would be gross. But if you multiply out the top, you would have some highest power of n, which would be n to the what? How many n's am I multiplying together if I multiply out n plus 2 to the n plus 1 times 2n plus 3 to the n? I'm going to get n plus 1 plus n n's. Gross, really gross. But so here's what I'm trying to say is you don't want to do it this way. But if you did, your first term here would be n to the n plus 1 times 2n to the n. Plus smaller terms. And if you do the same thing on the bottom, your first term would be 2n to the n plus 1 times n to the n plus smaller terms. And if you look at these two terms, they have the same degree. And the leading coefficient on top is 2 to the n. And the leading coefficient on the bottom is 2 to the n plus 1, which gives you a 1/2. Nobody should ever do this way. It's terrible. But it's possible. It's just not the way we do it because it's more work than we need to do. So the root test, use the root test. If you essentially have the sum from n equals 1 to infinity of a whole bunch of stuff raised to the nth power, or the n squared power, or the n cubed power, or something where it's going to simplify nicely when you take the nth root of it. But definitely not for things that don't. So like any of the other problems we've done with a factorial or anything, root test should only ever really be used in this one kind of special case. Yeah, time is it. Okay, we're good. Yeah, good time. So there's not a lot of other exciting examples for the root test though, meaning it's basically, oh, actually that's not true. I think I had one other one. Oh no, those are on the next page. We'll come back. Where'd you go? I had everything everywhere all at once. There we go. Cool. Sure. So let's look at this example. Look at the sum from n equals 1 to infinity of n plus 1 over 3 to the n. Okay, this seems like obviously a good candidate for the root test. So we're going to take the limit. It is good to mention what test you're using. So while this is a good candidate for the root test, I should point out what other test should be in the back of our mind. The nth term test. So I'm going to use the root test here because it's easy to apply. I feel like I'm writing this. That's fine. Yeah. And then the end of the 1 over n, those cancel out. You get the limit as n goes to infinity of n plus 1 over 3, which is going to be kind of the opposite, actually. N's going to infinity, so we have infinity divided by 3, which is still infinity, which is definitely bigger than 1. So in this particular case, we have divergence. Now, another way we could have seen this without actually doing the root test is by the nth term test. The nth term test here, if you just take the limit of the sequence, that thing is getting pretty, whoops, I'm getting ahead of myself there. That thing's getting pretty big. You've got something that's getting infinitely large to an infinitely large power. I'm pretty sure that's infinity. So you don't always have to use the test that seems the most obvious. In fact, I would strongly recommend keeping the nth term test in your mind. It's easy to, I didn't even think about it until I looked at this and I'm like, oh, we could have used the nth term test here. It's a good thing to keep in mind because sometimes there are things that are tricky, like the next example. Do I want to do that one next? Yeah, sure, why not? The sum from n equals 1 to infinity of 1 minus 1 over n to the nth power. This one, at first glance, looks like a great candidate for the nth root test. It seems like it, right? I mean, you got everything raised to the nth power, nth root test seems good to go. So the limit as n goes to infinity of the nth root of 1 minus 1 over n to the n is going to be the limit as n goes to infinity of 1 minus 1 over n, which is 1, which is inconclusive. The ratio test might work here. It might not. It seems like it'd be kind of a pain. You'd have 1 minus 1 over n plus 1 to the n, n plus 1 over 1 minus 1 over n to the n. That doesn't seem good. Here, what we need to remind ourselves of is the nth term test. We want to find the limit as n goes to infinity of 1 minus 1 over n to the n. Any guesses? Okay. So this is something we're going to see often enough that you want to get to the point where you don't have to use this whole e to the thing and then doing L'Hopital's rule. You're so close. It's almost e to the n. So this limit, I'm going to rewrite it like this. I'm going to write it as the limit as n goes to infinity of 1 plus negative 1 over n to the negative n to the negative 1. The reason I'm writing it specifically that way, I know it seems weird, right? You're like, why would you do that? Well, because there's this thing that kind of gets tossed around where we're like, we know that if you have the limit as x goes to infinity of 1 plus 1 over x to the x, it's equal to e. Or alternatively, the limit as x goes to 0 of 1 plus x to the 1 over x is equal to e. So the idea is we're trying to make it look like so that this thing here and this thing here are reciprocals. Because when that's the case, as long as this thing here is going to 0, whatever this is doing the reciprocal thing, it's going to infinity or sometimes negative infinity. This is going to work out so that this whole quantity is equal to e to the negative 1, right? If I ignore that, this limits e, and that's going to give me a negative 1. Now, this feels annoying somewhat because you're like, I don't want to rattle that. What I should say before we get too caught up here is that that would mean that this series diverges, because the limit of the nth term test is definitely not 0. So this diverges. Another example of this, which might be a little more palatable, would be, what if we had the sum from n equals 1 to infinity of 1 plus 3 over n to the n. This one's a little easier to justify automatically, that the terms can't go to 0. You have things that are bigger than 1 being raised to larger and larger powers. They definitely don't go to 0. But it is, I think, important for you to actually know what this limit is. Not that you don't already know it, but to see it. So let me show you the short way first. Let me show you the long way first, and then I'll show you the short way. So here's the long way. And again, I think after you do this a couple times, you don't really need to do this limit the long way every time. I think you want to get to the place where you can kind of be like, I know a shortcut, it's valid enough. Here's the long way. Limit as n goes to infinity of e to the natural log of 1 plus 3 over n to the n. And then we bring the n down in front of the natural log. So we get the limit as n goes to infinity of e to the n times natural log of 1 plus 3 over n. And then we bring the n down to the bottom. So we get the limit as n goes to infinity of, e to the natural log of 1 plus 3 over n over 1 over n. And then we use L'Hopital's rule, because the exponent here is a 0 over 0 type. You have natural log of 1, which is 0, over something that's going to 0. Using L'Hopital's rule, we get the limit as n goes to infinity of the derivative of natural log of 1 plus 3 over n is 1 over 1 plus 3 over n times the derivative of 3 over n, which is negative 3 over n squared, over the derivative of 1 over n, which is negative 1 over n squared. Questions? I know that I did, so just as a reminder, right, the derivative of 1 plus 3 over n is just the derivative of 1 plus 3 times n to the minus 1, which is negative 3 n to the negative second. And then the n squareds can cancel. Negative 3 over negative 1 is just 3. So I've got the limit as n goes to infinity of e to the 3 over 1 plus 3 over n. The 3 over n goes to 0, and we're left with e to the 3. That's the long way of doing this problem. The short way is the following. I'm going to write this as 1 plus 3 over n to the n over 3 to the third. Now I have an expression where I've got 1 plus a thing. That thing is going to 0, and the exponent is its reciprocal. If you've got that format, this inside part is going to e. So this entire limit is e to the third power. And so I guess I should just write very, very generally. So you want to take a picture? That the limit as some stuff goes to infinity of 1 plus 1 over the stuff to the reciprocal of the stuff, that's always going to be, oops, sorry. And so the stuff can be whatever you want, right? In this case, right, in this problem here, my stuff is n over 3. And so right, that's what I have. I have the limit as n over 3 goes to infinity, so n goes to infinity, of 1 plus 1 over n over 3, which is 3 over n, to the n over 3, that's going to be e. And you raise that all to the third power to get e cubed. It's not too awful, but it does. It's going to save you time eventually, because you're going to see this limit come up kind of over and over again. So you mean like when I have this 3 here? So that's coming from my adjustment. So let me give you one more example. So let's say we wanted to determine does this series I wanted to do a minus. I'll just make it a converge or diverge. And I will point out, if you did the nth root test, the limit would be 1, which would be inconclusive. So we're going to try the nth term test. Again, which means we think it diverges, right? Because you're only trying the nth term test. Well, you're really trying the nth term test just to like rule out that it doesn't work. But if it does work, great, divergence. So we're going to do the limit as n goes to infinity of 1 plus 2 over n to the negative n. And now what I'm going to try to do is I'm going to try and rewrite this so it's still the same, but looks like 1 plus a thing that's going to 0 raised to the reciprocal power of that thing that's going to 0. So I really, really, really want to write this as 1 plus 2 over n to the n over 2. But those aren't the same. So what outer power do I need to make it so this is the same as that? What negative number do I need up there as the power? Oh, you're so close. So when we have a power to a power, what happens to the powers? Like 2 to the 3rd to the 4th is 2 to the 12th. Did you multiply the powers? So I need a power to a power so that when I multiply those powers, I get that. So I actually need a power of -2. These are the same because n over 2 times -2 is equal to -n. But then this inside part is going to E. It has the exact right format. We could do all the long logarithm, bring down the thing, use L'Hopital's rule. We're not gonna though, because it has the right form. It's 1 plus a thing that's going to 0 raised to a power that's getting infinitely large. So this is going to be e to the -2, which I'll remind you again, isn't 0. So we get divergence. Question? Right. Well, so just to back up, we did. So, right, because when we wrote it, right, we had 1 plus 3 over n to the n, and then we rewrote it as 1 plus 3 over n to the n over 3. Oh, sorry, apologies. So we had this, and then we said, oh, I really want this power to be the reciprocal of that power. So I made it an n over 3, and then raised it to the 3rd power to adjust for that division by 3.
That's the way to show it, but otherwise it would just be like e to the power of that, like if n. Okay, so if you have n in the denominator, like you do, like yeah, there, and then you have n, and then you raise it to the power of n, so it's just e to that numerator.
Yes. Yeah. So yes, you could totally say that the limit as n goes to infinity of 1 plus any number you like over n to the nth power is going to equal e to the a. I think that's what you're saying, right? Yeah, definitely, 100%.
So for this problem, could you just like do 1 plus 2 over n to the n, and then raise that to -1, and then get that?
I think so. Yeah. Yeah. Oh, I see what you're saying. Totally. Yeah. You could, yes, you could definitely see it that way. You could definitely rewrite this as the limit as n goes to infinity of 1 plus 2 over n to the n to the -1, and then use the thing we just said to say that, oh yeah, this inside part is going to e squared. So that's going to be e squared to the -1, which is e to the -2. I personally prefer to write it as specifically 1 plus thing and then the powers of typical thing, but you're totally 100% right. If you want to write it as 1 plus thing to the nth power and then just recognize that it's going to be e to that number there, you're good to go. Just be careful. Be aware that if there's a minus sign there, it's going to be, you really have 1 plus -2/n. So it's going to end up being e to the -2/n. Yeah, you're totally right. Good. That's a good observation. Okay, let's. Sure. What time is it? Okay, we got not a lot of time. So let's look at a couple more examples. Let's say we have the following: the sum from n equals 1 to infinity of n to the 2n over 2n squared. I feel like you could use the ratio or the root test here, but I think you should use the root test if you can. Meaning, if you got things raised to the nth power or the n squared or the n cubed or the n to some power, root test is probably going to be the easiest to use. So if we try the root test here, we're going to get the limit as n goes to infinity. And I really do think it's our best interest is to write it as our a sub n term to the 1 over n power. And then we have a power to a power, we multiply those powers. So we're going to get the limit as n goes to infinity of n to the 2n times 1 over n, which we should just say that's 2, over 2 to the n squared times 1 over n. And then doing the simplification we probably should have done already. N to the 2n times 1 over n is just n squared, and 2 to the n squared times 1 over n is just 2 to the n. Ooh, what's the limit of that? Okay, n squared over 2 to the n. I think there are a couple ways you can justify this yourself. One way, we know exponential functions outpace polynomial functions. 2 to the n is definitely going to be way bigger than n squared eventually. So that's one way of just saying, I know that limit's going to be 0. But if you wanted to be a little more rigorous, you could use L'Hopital's rule twice. That would also get you there. So remember that the derivative of 2 to the n is 2 to the n times natural log of 2. But a lot of people at this stage would probably be totally fine with you just saying, yeah, I know that's 0 because the bottom thing is a bigger function than the top thing. Yeah. Sure. Something that might come up, I just want to make sure you all know, is that the limit as n goes to infinity of the nth root of n is 1. It seems maybe not super intuitive. Like, it doesn't feel exactly counterintuitive, but it's not super intuitive either, that limit would necessarily be 1. You've got something bigger and bigger and bigger, but you've got a power that's getting smaller and smaller and smaller. I feel like it's, so this one, to be perfectly honest, this is something that always kind of perplexed me when I was like, really? That's 1? Like, really? Are you sure? Let's show it the way we usually show limits involving exponential things, by doing the e to the natural log and then using L'Hopital's rule. So let's take a quick look. I do think this is worth actually seeing because, like, it's good to believe it. You'll probably have to use it a couple times, but actually knowing in your heart that it is true is a good thing to know. So I want to take the limit of this, and I'm going to rewrite it as the limit of e to the natural log of n to the 1 over n. And this one actually simplifies pretty easily. You get the limit as n goes to infinity of e to the 1 over n times natural log of n, which I'm going to write as the natural log of n over n. I brought the 1 over n down in front. 1 over n times natural log of n is just natural log of n over n. And now this exponent is right, that's an infinity over infinity type. So we can use L'Hopital's rule. The limit as n goes to infinity of e to the derivative of the natural log of n is 1 over n. The derivative of n is 1. Oh yeah, this seems not too terrible now that you actually say it. 1 over n goes to 0, so we get e to the 0, which is 1. So it really is the case that this limit is equal to 1. Yeah. No, you can't. The problem, and that's a very, very astute question, but it's actually the case that infinity to the 0 is another indeterminate form, which means it could actually take on any value. Now, I will tell you, most of the time, when you have an infinity to the 0th power or a 0 to the 0th power, which is also an indeterminate form, like 99 times out of 100, it's going to end up being 1. But there are examples where it's not equal to 1. So it doesn't always end up being 1. If you had to guess, you should just guess 1, right? Like if you see something that's like something raised to something that's going to the 0, it's a pretty good bet that it's equal to 1. But there are some counterexamples. For example, this limit. The limit as n goes to, I have to remember what it is now. Grant and I came up with this limit a while ago. Oh gosh, sorry. Infinity, maybe. I think it's, oh yeah, I think it's n to the 1 over the natural log of n. That seems good. Yeah. Oops, you want to see the thing, maybe? Yeah. So let's see. This is an infinity to the 0 type. I'm pretty confident it's not 1. This one's at, yeah. This one, Grant came up with this one. I should give him all the credit. He was very clever. Like, oh yeah, what about this, James? So let's see what happens if we do the thing. If we do e to the natural log of n to the 1 over natural log of n, look what happens. The 1 over natural log of n power comes down in front. So you get the limit as n goes to infinity of e to the 1 over natural log of n times natural log of n. Those cancel. So you have the limit as n goes to infinity of e to the 1, which is e. So it is possible for an infinity to the 0 type to not have a limit that's 1. But you ask a very good question, because most of the time, unless someone's really trying hard to make up something that works, that limit is going to be 0, or it's 1, sorry. We probably shouldn't start talking about a new test. Let's go ahead and look at, sure. One more example. Yeah, so let's look at actually this example. The sum from n equals 2 to infinity of n over natural log of n to the n. So even though I said a thing before, it's not always 100% of the time true. This is another example where you actually would probably try using the root test, even though the entire thing isn't raised to the nth power. Usually that's when we use it, but you are some counterexamples or some situations where you want to use it, even if you don't have the ideal situation. I will point out, ratio test here is awful. No, we don't want to do the limit as n goes to infinity of n plus 1 over the natural log of n plus 1 to the n plus 1 times natural log of n to the n over. That seems real dicey. So if things look, I mean, sometimes things are gross, but if they look really gross, it's probably not a bad idea to think of trying something else. We can always come back to this and be like, well, it looks gross, but what's what we've got? But instead, let's try the root test here. So the limit as n goes to infinity of, I'm just going to throw the root test at it. So I've got n over natural log of n to the n to the 1 over n. And distributing the power, I have n to the 1 over n over the natural log of n. Okay, so now we're going to actually look at this separately. Where's the top going to? Right. Where's the bottom going to? So that limit's 0. And then you have to remember what it means, right? We've taken all these limits and they're like, why are we doing this? What is it telling us? So remember, this 0 is like your ratio. And if that ratio is less than 1, then this series converges. And yeah, we definitely shouldn't start talking about new things. I think we can stop there at 258. It's not too terrible to end early. Next time, we'll start talking about the alternating series test for absolute convergence, maybe conditional convergence, and maybe start talking about power series. So those are definitely what's on deck. But for now, what I'll leave you with is remember that the ratio test and the root test are virtually the same. If the limit that you're taking is larger than 1, you get divergence. The limit you're taking is less than 1, you get convergence.